Swayam Prabha. Digital India. Educated India.
Welcome back. We're going to talk about synthesis. We did some examples. We're just going to do synthesis, two-step synthesis on the same molecule. So this wheel is not really a reaction wheel. It's more like a short synthesis wheel. All right. Okay, well, what do we do when we do synthesis? Again, we have some synthesis strategies that we follow. One, as it says here, find the starting material in your product. One thing you could do is take like a highlighter, not a red one, but any other color, and try to outline the fragment of the starting material that remains in the product. That's one thing you could do. So then the rest of it is just checking to see, was there a skeletal change? Was there a functional group change? And then you work backwards and bring in the reagents. We got to pay attention to regiochemistry and stereochemistry. That's really important, because in a synthesis, you have to run with the major product. You can't run with the minor product, okay? It's almost like when you bake a cake and then you have a leftover batter and you make a couple of cupcakes. You can't just take the whole thing and throw the cake out and eat the cupcakes, right? Doesn't make sense. Same here. You got to go with the major. So in every one of them, regiochemistry is really key. And then stereochemistry should be, the way it's specified. Is it syn or anti in most cases? Or is it non-stereo specific, which means you can get above and below. Regiochemistry, does it prefer one side of the pi bond, or the triple bond, or the double bond, or does it prefer one side of the carbonyl, or something that it's attacking? So we got to pay attention to all of those details. It's not just bringing the reagents in and saying, okay, here, deal with this. We just have to make sure the end product is exactly what is specified. Let's go from the top, just like the clock. Here we have a 5-membered ring, great. What about this guy? What happened to that little methyl group sticking out? It's gone. So here we have a skeletal change. Skeletal change, when we had skeletal changes, we got to think, well, was it came in for oxidation? Is it combustion? Is it a ozonolysis? So all of those are possible. So we severed a bond right here, and so we don't have that. So one of the carbons is missing. One of the things we could do is find out how to make a carbonyl from a 5-membered ring like this. If you're going the ozonolysis pathway, we need to have a double bond for it to sever. So working backwards, because we lost a carbon, most probably that carbon was attached here, and during ozonolysis, it got chopped off. So you have here a CH2, and ozonolysis is going to cut this in two and put oxygens on both sides, which means this is going to go as carbon dioxide. Now over here, whenever you do ozonolysis, all you're doing is cutting this out and putting an oxygen right there where the pi bond is. So you don't take away the pi bond. The double bond is still there, except it's ending on an oxygen now and not a carbon. So this ozonolysis would obviously require O3-DMS. Let's look at how you can get to this alkene from here. Here's a tertiary. If you do a E2 on a tertiary, most probably you would get a nicely substituted alkene right here. That's diazephrol. right? So if you don't want a Zaitsev, so here the alkene is outside, which means you don't want a Zaitsev. And what's the opposite of that? Opposite of Zaitsev is Hofmann. And how did we do a Hofmann? We brought in a very huge base. Potassium terbutoxide would probably give entirely a Hofmann product. So you want to remove this HI here. And so therefore you would bring in T-butoxide, DBU, DBN, so a bulky base. And here you can have it in the protic solvent there for the E2. Okay, so this is Hofmann or anti-Zaitsev elimination, E2. Great. Let's go to the next one. All right, so here we have all of our carbons intact. We didn't do a skeletal rearrangement, or we didn't somehow take apart our ring or our carbons. Everything's intact. But functional group changes, yeah, we have it. We got an iodine going to a hydroxyl, right? How did that happen? Abracadabra, wham. You got your hydroxyl. We just have to go stepwise. Work backwards. Okay, your hydroxyl is not where the iodine is. If it was right here, that would have been too easy. You just treat it with some water and acid and you would get a nice SN1 here. But obviously it's not there. If you had put your hydroxyl right here, that would have been Markovnikov, right? You take this off, carbocation forms in the most substituted place, which is a tertiary. Hit it with water, deprotonate, and get a nice alcohol. Do you see that here? You don't. So therefore, this is probably going to be an anti-Markovnikov addition to a alkene. And where should the alkene be? Obviously, it has to be between these two carbons. Now, I could have put the hydroxyl here. It would have been identical because if you just flipped it over, it would have been right there. So this is an anti-Markovnikov addition. Let's write that down. And then we can see how many ways we did an anti-Markovnikov addition. Do you recall? One of the first things we did was a BH3 addition. BH3, and especially if you have two R groups on boron, R2BH, then it's going to be very, very regioselective and go to the carbon that's less substituted. Okay? Even though they don't show stereochemistry, it is going to be anti-addition. So you could do this. If this is on top, this would be at the bottom. So it is very stereospecific and regioselective. And there are very few reactions that were both stereospecific and regioselective, and BH3 addition was one of them. So we can do R2BH, and R2BH can be 9-BBN, and it comes with THF, and then you oxidize that with peroxide in the presence of a base. And we went over this mechanism. And you know, here when you have a synthesis question, we don't really do a mechanism. We just look at what's changed and bring in the reagents. But sometimes if you have to think it over, just have a scratch paper and do the mechanism on the side kind of quickly, just to make sure that the stereochemistry and the regiochemistry are correct. For some students, they have to do the mechanism to do the synthesis, but it does take time. But you would see if you do more and more of them, it'll be a lot quicker as time goes. All right, so that means we need to have a double bond right there, as we said before. And how would you make a double bond right there? This is tertiary. Even with sodium hydroxide, it's not going to do an SN2. It's going to do E2. So therefore, you can put a small base here. So small base could be sodium hydroxide or sodium methoxide. A small base would do it. What would be the solvent? Well, we're going to have THF here. Why don't we use the same thing here? THF, tetrahydrofuran. Okay. All right. Or you can have other aprotic solvents as well. If you have protic solvents, you may have a slight amount of SN1, but you're going to have mostly E2. All right. Moving along. Let's go over here. Oh, a lot more changes. It's not just like one thing now. There are two things here. And one of them is an ether bond and one of them is a chloro. Well, let's look at the stereochemistry here. They are anti. Now, do you recall doing anti-additions when you had halogens? So that's one of the things that we talked about. When you had a halogen like this, you had anti-attack all the time. So if you have an X, then your incoming group came in anti to that. And this could be ROH or RH2O or some protic solvent, even amines, all of this would work. Now, this is going to go over here more than here if it's substituted. So therefore, you are going to have a alkene now to do a chloronium, and then you would open it up with methanol. And the methanol will deprotonate it and make it neutral. So here, the important thing is the precursor to this has to be an alkene. Okay? And in this case, the double bond should be then right here, which is the same as this. I'm just drawing it in a different position, but it's the same molecule. Sorry, methyl cyclopentene. This is also methyl cyclopentene. Okay, as long as the carbon that's most substituted has the alkene, they are both the same molecule. All right, so now that we have this, we know we can put chlorine in here to give you the chloronium, Cl+, and then you do that in the presence of methanol in a protic solvent. If you had other R group, let's say you had isopropyl here, then you'll bring isopropanol. Let's say you had an amine here, let's say NHCH3, then you bring in CH3NH2 here. So whatever the group here, bring it with a protic solvent. If you had it as a methoxide, then it's going to go over and attack the less substituted. So it has to be protic. All right. So there you go. Again, how do you go from here to here? This is tertiary. SN2 is impossible. We can use a small base. Why not use sodium methoxide here? And it could be in methanol. And you can add that. So you do an E2 here. The more you heat it, the more E2 you would get, and the less SN1 you would get. And then you would do a very nice alkene, chloronium it, and hammer that onto the more substituted carbon, because we said this was a Markovnikov addition. Whenever you have a positive charge here on the top, like if you had Ag plus, Br plus, Cl plus, or oxygen with a positive, all of this would do Markovnikov addition and add that protic solvent or the protic nucleophile, which is a weak nucleophile, to the more substituted carbon. That's key. Okay, so this is Markovnikov. That's really important. All right, moving along, let's go to this one. Oh, whatever happened to this? It doesn't look anything like it. How do you, and what is this? Is that an alcohol? COH? A lot of people think that, okay, but we have to draw it out. If it had been an alcohol, then it would have looked like this. You put COH here, well, you wouldn't have enough electrons for that carbon. So therefore, this is not an alcohol. This is going to be an aldehyde. That's right. So whenever you see CHO, this is what they mean. This is CHO. Okay, that's really important. It's a common mistake. Now, there are two carbonyls here. How do you think we got two carbonyls? We saw that before. We had over here two carbonyls as well. And we took that out and we said this carbon is hooked to this. And so there must be a pi bond. So if you have two carbonyls on the same chain, the starting material that it's most probably coming from had a double bond between these two carbons. So take the two oxygens off and put a pi between them. So just to kind of make it easy, I'm going to draw this weird structure. Just keep everything the same. And then put a pi bond between this carbon and this carbon. You see? 1, 2, 3, 4, 5 in the ring. So that is going to be 1, 2, 3, 4, 5. And then a metal sticking out, which you need to have. And that's the pi bond. Okay? So the pi got severed into 2 carbonyls. So 2 carbonyls on a chain. Think. Ozonolysis. All right, so put 2 oxygens here, and you're well on your way. All right, let's go to the next one then. How do you make a double bond here? We've done this here, we've done this here. I ain't gonna beat you out on that. And let's put a small base. Let's put ethoxide. And it comes in the solvent. And because the ethoxide is so much more powerful than a neutral solvent, it's going to do E2 and give you the Zaitsev alkene. SN1 is going to be hardly anything there, okay, because this is more powerful than this. And if you heat it up with all that entropy, you would get more and more E2. And this is going to be Zaitsev. And it's the same here. Now, here we go. We got pretty much the same thing as over here, but instead of an OH, we have a longer chain. How did that happen? Can we do a anti-Markovnikov here with methanol and put it over here? What do you think? Well, if you had H2SO4 and ethanol, it's definitely going to go over here. It's going to be Markovnikov. So we have to do an anti-Markovnikov addition, and then we can do a R group on there. That's one way to think about it. If you had an epoxide and opened it up, you would have 2 oxygens. You don't see that, and you don't see a chlorine or a halogen. You could do mercury, but in that case, this would have attacked here because even oxymercuration, demercuration is going to be Markovnikov. So there is no way this is going to go through some Markovnikov process. It's got to be anti-Markovnikov, and it is on opposite sides. And the only thing we saw that was anti-Markovnikov and anti-stereospecific was BH3, that's correct. So we are going to do the same BH3 here. So we would have an intermediate here where you are going to have your BH3 add, and then you're going to oxidize it. But then your alcohol would have to then go into a ether. How do you convert an alcohol to an ether? Let's put an extra step for that. Or you could write 1 and then 2 and do it. Well, in this case, if you take the alcohol that comes out of here, that is going to be anti to this. So if you put a BH3 THF, and then you put in H2O2 OH minus, and it's aqueous, you're going to get your OH here. Now you got to take that hydrogen off and put an alkyl group. And we saw that in a previous synthesis, the best way to take this off is with a base. We can do, let's say, sodium hydroxide, or sodium hydride is even better. And then you get an anion, and then you do an SN2, and this is going to be really easy to do an SN2 because it's primary. All right, so let's take that hydrogen off with sodium hydride first. Then you can put in your ethyl chloride, or bromide, or iodide. So your anion, the hydride takes this off, makes this into an anion, sodium alkoxide. That's going to do an SN2 over here. Great, so you know how to make ethers, alcohols, chloroethers. You can make aldehydes and ketones. You can see why alkenes are such a huge part of your life. Let's take this. We got 2 OHs. We did 1 OH, but now we got 2. And they are stereospecific. They're syn. So we did anti-diol and syn-diol. This is a syn-diol. So in order for these 2 hydroxyls to be hanging on to there, you need an osmium tetroxide hanging on to a monkey bar, which is an alkene. So over here, you should have had an alkene right here. So you would have an alkene right here, and you would have osmium tetroxide, OSO4, NMO, and then work up with some NaHSO3, and so there you go. You got your double whammy diol. Well, you've done the internal alkene many, many times, and it's just a small base, and we pretty much done most of our small bases, sodium hydroxide and so on, and heat. All right, so that's a syn-diol. So we are paying attention to the stereochemistry. It can get attacked from above or below, and that's why we have the plus and minus. We get 2 enantiomers because this is not a meso. Because of the methyl, you have a chiral center here and here. They don't have a plane of symmetry. Therefore, it's not meso, and it's chiral. So you can get plus and minus attacking on top or bottom. So whenever you see plus and minus, it means you have stereoisomers. And here, if you have plus and minus, and it's a raceme, that means you don't have any stereoselectivity. All of these, when you say plus and minus, it means you don't have any stereoselectivity. They're equal. Let's look at this. Now, here the hydroxyls are on opposite directions. So, well, we can't do the same thing, but we do have to put 2 OHs. How are we going to do that? Anti-addition. And whenever we had anti-addition was associated with some kind of a triangular form. So, note anti-stereospecificity. Think triangle with some group there, delta plus. Because that's the only way you block one face and you hammer it from the opposite face. All right? So having a triangle would be key to anti. So since this is anti, what would be the triangle? In a diol, you got to have one of the oxygens holding it and the other one coming in. And here it says O18. So that's typically what we do when we want to add a deuterated water and open up a epoxide. So here you have an epoxide, and the epoxide is going to attack, and it's going to attack at the most substituted carbon because it's going to happen in acidic solution. So you'll have an O18, and you can do that with an O18 water attacking and opening that up. So your intermediate here is going to have a 3-membered ring, an epoxide. And let's draw that in. And your methyl will be here, and it can be up or down. The important thing is that the incoming group is going to go anti. So you would have some acid that are protonated, and then you will open it up with OH2 18, deuterated water, and that's going to go in the Markovnikov. All right? So let's bring in the reagents. How do you make an epoxide? Take an alkene and put MCPBA on it or some peroxide on it. And what kind of alkene? Internal alkene, not external. It's on here. So this is the same as this or this or this. So we can use a small base for that. So if you use a small base for that, let's say 1 NaOET in, let's say, a protic solvent. So 2 would be MCPBA, metachloropobenzoic acid, in some aprotic solvent. Then you would have to protonate that, and then you would do the addition here. So for that, let's say you have HCl. Okay, so that's going to give you a labeled oxygen 18 here. All right, so we're getting up there now. So when you have anti-addition, think triangle. In this case, you have an oxygen, so you have an epoxide. Then you're going to open that epoxide Markovnikov because it's in a protonated protic environment. You want to form the most stable, most substituted incipient carbocation here, which is why it's going to attack here. So this is a Markovnikov. So there is regiochemistry to this as well as stereochemistry. Same here, you have regiochemistry here and then stereochemistry followed by that. And here too, if your epoxide has formed at the bottom and the methyl's up, then you're going to get attack from below and you would get the other opposite enantiomer or the mirror image. So that's why you have a plus minus raceme. All right, let's go on to the last one. Here's one. We put an alcohol on the very edge of the molecule. We did that before, but we put it inside. And here we're putting it right outside. So it's going on the less substituted, which means it's anti-Markovnikov. Good, and we know anti-Markovnikov hydroxyl additions are through borohydration. Very good. Now, there's also another thing. Not only is it outside, it's also on the alkene should also be external. It can be inside the ring. So therefore, you have both anti-Markovnikov as well as anti-Zaitsev, because if you're putting your hydroxyl here, you're going to have a pi bond there. So for the anti-Markovnikov to happen. So you would have a pi bond outside. That means you're going to have a Hofmann elimination, and we did that right next door. So you'll have a huge base, and you'll do that, and then you're going to do an anti-Markovnikov. So here's an anti-Zaitsev and anti-Markovnikov, all anti, all right? So first you bring in a large base. Let's say we have DBU, DBN, and then of course you have to then wash it out and do some hydrolysis to get rid of all of that, and you will get an alkene. So this is going to be an E2, and it's going to be a Hofmann E2. So this is Hofmann, and this is also a Hofmann. Now that you have an alkene, external alkene here, less substituted alkene here, now you have to put in your hydroxyl also on the less substituted, and that is going to go with, let's say in this case, we're going to use BH, R2BH, and let's say we have 9BBN. And then on this side too. So that's 9BBN. And then you oxidize this just like you would do with BH3 with a base and water, H2O and NaOH. All right, so you're getting anti-Zaitsev, anti-Markovnikov. I'll write that down, anti-Markovnikov, anti-Zaitsev, which is Hofmann. All right, and here it doesn't matter whether it's going to be up or down because it's achiral. However, whenever you have chirality, it's typically a raceme. Here is a chiral molecule, so you're going to get a raceme. Why? Because in this case, your BH3 can go above, pushing the methyl down, or your BH3 can go below, pushing the methyl up. So you would get mirror images here. This is a chiral molecule. Therefore, chances of those happening are almost equal because it's a flat sp2 pi bond. So therefore, you'll have almost a 1-to-1 raceme. Okay. Here again, you have a plus minus, and this is also going to be a raceme. Once you form your alkene, your chlorine can go up or down. And the methanol can attack on the opposite side of the chlorine, Markovnikov on the more substituted position. So there's regiochemistry and stereospecificity, and you would get a raceme, a 1-to-1. Again, as I said, it's a pi bond that's flat. You can form the chlorine up and down equally well. All right, and here when you have carbonyls are flat, so you don't make chiral centers. Over here you have again plus or minus raceme, and this is also because you have an alkene that's flat. BH3 can attack above or below because it's a flat pi bond. and therefore you can have the oxygen or hydroxyl forming after the oxidation on the opposite side of the methyl. That's the important thing. So that's why this chiral molecule would have a 1-to-1 raceme. Same here, you would have a pi bond, osmium tetroxide can attack above and below equally. There's nothing really favoring it from attacking above or below. They're both equal. So there's no stereoselectivity. So you have a plus minus raceme. That means it's a 1-to-1. Same here. When you add the MCPBA, it can form above or below. The important thing is it's going to form on the opposite side of the methyl. Therefore, when you open it up, you're going to open it up Markovnikov, and it's going to come from the opposite side of the epoxide. Just because the epoxide is blocking the top, it has to come in from the bottom. So whenever you have a triangle, your nucleophile is going to attack on the opposite side. If it's in a protic environment, it will be Markovnikov. If it's in an anionic environment, it would be anti-Markovnikov. Here is protic, so it's opening it up here to give you anti, and that's going to be a raceme, just because you have an equal opportunity to form this up and down in a 1-to-1. And here again, you have a DBU, an E2 that's Hoffman, and then you have an anti-Markovnikov addition, adding your hydroxyl here. There is no chirality here because if you add your hydrogen, you can add your hydrogen here, and it's really not creating a chiral center. So therefore, this is achiral, and it really doesn't matter whether it's up or down. So as you can see, synthesis can be packed with a lot of regiochemical and stereochemical information. It's best to work backwards, because once you start working in one direction, you might end up with the wrong one. So therefore, when you go in reverse, then you're going to be very specific about your reagents, and you wouldn't waste time. That's one way to save time on an exam, guys, is work backwards. But make sure that you have the stereospecificity and the regiospecificity nailed. All right, I'll talk to you soon. We'll come back with some more stereospecific synthesis, a little bit more complicated than this. If you thought this was complicated, wait till you see the next one. Talk to you soon, guys. Bye.